Discuss is gas exchange, and gas exchange refers to the movement of gases, particularly oxygen and carbon dioxide, across the alveolar and capillary walls. So exchanging oxygen and carbon dioxide between blood and the alveolar space. Now, despite the fact that this is such a critical part of external respiration, gas exchange is accomplished entirely via passive diffusion. And previously, when we've discussed passive diffusion, we've talked about it as going down a concentration gradient. Now, for gases, we don't talk about concentration gradients. What we actually talk about is something called a partial pressure gradient. So let's talk about what a partial pressure gradient is. So the pressure of a gas actually is a measure of the concentration of a gas. So this is the analogy. So in atmospheric air, we don't have just one type of gas. In fact, it's a mixture of gases, primarily nitrogen and oxygen. So 79% of any amount of atmospheric air, any volume of atmospheric air, 79% of that is composed of nitrogen. 21% is composed of oxygen. Okay? And then we have trace amounts of other gases, carbon dioxide, humidified air, so water vapor, H2O, and trace amounts of other gases. Okay? And so we don't really consider that in terms of a full percentage point, since it's really just very, very small amounts. So the total pressure at sea level for atmospheric air is what we call atmospheric pressure, which, like I said, at sea level is 760 millimeters of mercury, and millimeters of mercury is a measure of pressure. Okay. So total pressure is atmospheric pressure, 760. Now, what we want to understand is the individual contributions toward total pressure that these different gases that make up the mixture of gas contribute. Okay, because the percentage of pressure that they contribute is going to be related to their concentration. Okay, so the partial pressure, which is a measure of that, is calculated actually very, very simply. Since all gases in a mixture exert the same amount of pressure, we can understand the specific pressure exerted by a particular gas in a mixture by just multiplying the total pressure by the percentage of the percentage that gas contributes to the total amount of gas. Okay. So, for example, nitrogen is 79% of atmospheric air. So the partial pressure of nitrogen simply is equal to 79% times 760 millimeters of mercury, total atmospheric pressure. And so we get a partial pressure for nitrogen equal to 600 millimeters of mercury. Okay. And so the partial pressure of nitrogen is sometimes written as a capital P with a subscript of the particular gas. So for the partial pressure of nitrogen, it would be P sub N2. Okay? And that, as I said, equals 600 millimeters of mercury. Now, oxygen is obviously the gas that we care the most about in terms of gas exchange. So the partial pressure for oxygen in atmospheric air is equal to 21% times 760 millimeters of mercury, which gives us 160. So the PO2, which denotes the partial pressure of oxygen, is equal to 160 millimeters of mercury. Okay? And we said that there is a trace amount of carbon dioxide in the atmosphere, so the PCO2 the PCO2, or the partial pressure of carbon dioxide in atmospheric pressure, is 0.03 millimeters of mercury. So you can see it's really very, very small. So when we're talking about the process of gas exchange, what we're really talking about as I said previously, is the passive diffusion of gases between the alveolar space and the blood. And since we're trying to get oxygen from the alveolar space into the blood, then the partial pressure for oxygen in the alveolar space must be higher than the partial pressure of oxygen in the blood at the site of gas exchange. Okay? And vice versa must be true for carbon dioxide. The partial pressure of carbon dioxide in the blood must be higher than the partial pressure of carbon dioxide excuse me, in the alveolar space, okay, to promote the movement in that direction. So let's look at the partial pressure of oxygen going from atmospheric air and then working our way toward the alveolar space, which is the site of gas exchange. So the partial pressure of oxygen in atmospheric air is 160 millimeters of mercury. Now, once we take in a big breath, that oxygen actually mixes with some water vapor that is contained in our airways and in our lungs. Okay? And this water vapor in our lungs has a partial pressure of about 47 millimeters of mercury. So this water vapor is very, very important in our respiratory system. The water vapor humidifies the air in our respiratory system, and it keeps our membranes moist, and it maintains the health of the airways. So the partial pressure of the water vapor, the pH2O, is about 47 millimeters of mercury. That's going to dilute the air that we take in when we breathe in. So the previous partial pressure of nitrogen was 600, now it's diluted to 563. Partial pressure of oxygen was 160. Now in the airways and in the lungs, it dilutes to 150. Okay, so already we've gone from 160 to 150. Now when that breath is taken in even more deeply, okay, and it gets all the way to the sites of gas exchange, the sites where we actually have the movement of oxygen and carbon dioxide to and from, which is at the alveolar sacs, what we see is actually another dilution of the PO2 in that air. So the PO2 of air that gets into our lungs went down to 150 millimeters of mercury. But once it distributes itself throughout the alveolar sacs, it actually dilutes again. It goes down to a PO2 of 100. And the reason why the PO2 drops is because the air in the alveolar sacs do not completely refresh with every breath. In fact, only about 15% of the air in the alveolar sacs when we're breathing quietly actually is composed of freshly inspired air, or this newly inspired air. So the air that comes in gets diluted by the air that was taken in by previous breaths. And that air is going to have a higher carbon dioxide concentration because the carbon dioxide is moving from the blood into that alveolar space. So when we finally get to the site of gas exchange, the PO2, the partial pressure of oxygen, is sitting at 100 millimeters of mercury. Okay? So that's an important value. So here we're going to be talking about what the partial pressure gradients actually look like for oxygen and carbon dioxide at the site of gas exchange. And so in this cartoon here, the blue box at the top represents atmospheric air, where the PO2 is 160 millimeters of mercury. We take in a breath, and this, what looks like a pink jug, represents our airways at the top, and then all of our alveolar spaces at the bottom. So you can see we take in a breath, which is illustrated by the green arrow, and immediately PO2 drops to 150. And then that breath is taken in more deeply, and it mixes with previously inspired air at the alveolar sacs, and it is diluted again down to a PO2 of 100. Okay. Now, over here on the bottom of the slide, we've got the heart, okay, and what looks like a tube that is running in a circle around the heart. What this is meant to represent is the pulmonary circulation. Okay, so on the left side we have the pulmonary artery leading to this part of the slide, which represents all of the pulmonary capillaries. And then on the right side, leading back to the heart, is the pulmonary vein. Okay. So deoxygenated blood, which is really only relatively deoxygenated, not fully deoxygenated, deoxygenated blood that leaves the heart by the pulmonary artery and then perfuses the pulmonary capillaries has a PO2 of 40 millimeters of mercury. Okay. So at the site of gas exchange, right, the interface between the alveoli and the pulmonary capillaries, the partial pressure gradient for oxygen movement is 100 in the alveolar space compared to 40 millimeters of mercury in the pulmonary capillary space. So the magnitude of this partial pressure gradient is the difference between those two values, which is 60 millimeters of mercury. And that's a fairly sizable partial pressure gradient. Okay. So oxygen starts to move in the direction of the lower partial pressure gradient. So oxygen moves into the capillaries. Okay. And it's going to continue to move until the partial pressures on both sides are equal. So the pulmonary capillary blood is raised from a PO2 of 40 to a PO2 of 100. And PO2 of 100 is oxygenated blood, represents oxygenated blood going back to the heart through the pulmonary vein. And as you can see, the heart is then passing that blood onto systemic circulation. Okay. For carbon dioxide, it's a slightly different story. So looking at the blood end of it first, the pulmonary artery delivers relatively deoxygenated blood, and blood that has a PCO2 that is relatively high. And the partial pressure of CO2 in this relatively deoxygenated blood is 46 millimeters of mercury. If we look, however, at the PO2 of the air in the alveoli, it actually is quite high compared to atmospheric air, right, which is up here. So atmospheric air has a PCO2 of 0.03, but the alveolar space has a PCO2 of 40. Okay. So that PCO2 is actually quite high in the alveolar space, and that's because, again, only 15% of the air in that space is freshly inspired air, right? The rest of it, 85%, is previously inspired air, which has carbon dioxide that's been collecting. Okay. So if we look at the partial pressure gradient for CO2, we have at the blood level a PCO2 of 46, in the alveoli a PCO2 of 40. Okay. And so if we subtract those two numbers, we get a magnitude of this gradient that is equal to 6 millimeters of mercury, which is much smaller than the gradient that we saw for oxygen. Okay. So CO2 is going to move out of the blood into the alveolar space, okay, until the blood PCO2 drops to 40. Okay. Now, oxygenated blood that's leaving the lungs and returning to the heart through the pulmonary vein has a PCO2 of 40. And so the PCO2 of oxygenated blood of 40 is actually much higher than atmospheric PCO2. And so there's an interesting explanation as to why our body actually holds on to a considerable amount of CO2 compared to what we see in the environment. And we'll talk about that in a little bit, but basically CO2 in the body is contributing to our body's ability to balance and maintain a healthy pH in our plasma. Okay? So CO2 in our blood is actually contributing to pH balance. Okay? So that's why we actually hold on to much more CO2 than you'd expect compared to atmospheric. So since gas exchange occurs entirely through passive simple diffusion, and it's such an important part of external respiration, actually you don't get anything happening after that with external respiration if you don't have gas exchange. So the lungs are actually very, very adapted, highly adapted to maximize this gas exchange, maximize diffusion. So there's a basic equation that measures or determines the amount of gas that is transported, or what might be a better way to say that, less confusing, because we talk about gas transport later in terms of moving through the blood. But we could actually describe this as the amount of gas that's diffusing or gas that's being exchanged. Okay? So the amount of gas that's diffusing or being exchanged is equal to the surface area available, right, for diffusion times the size of the partial pressure gradient, and then inversely proportional or divided by the thickness of the diffusion barrier. So immediately we recognize that here we have three aspects of Fick's law, right? Fick's law was the several characteristics that will determine the rate at which diffusion occurs. And here are three of these Fick's law parameters. The surface area available for diffusion, as that increases, the amount of gas that's exchanged increases. The size of the partial pressure gradient, which as that increases, also gas exchange increases. And then the thickness of the diffusion barrier is, as that increases, that actually causes the amount of gas exchange to be reduced. Okay? So three very important parameters, and as we'll see in the next couple slides, the lungs are highly adapted to maximize these factors, right, or minimize in the case of thickness of the barrier, in order to maximize diffusion at the site of gas exchange. So first of all, the surface area available for gas exchange. The surface area in both lungs total is about 75 square meters of surface area available for gas exchange. And just to give you some perspective on that, 75 meters squared is about the area of a tennis court. Okay? So the reason why we are able to fit such a vast amount of surface area available for gas exchange in our lungs is because of the arrangement of the lungs. The fact that we have this pattern where our airways branch multiple times into smaller and smaller airways that eventually lead to a multitude of alveolar sacs. That anatomy is what is allowing for this significant amount of surface area to actually fit within our thoracic cavity. Okay? If our lungs were simply hollow sacs of air and the perimeter of these hollow sacs were the only sites for gas exchange, the surface area available would drop to about 0.1 meters squared. Okay? So we've managed through the anatomy or the structure of our respiratory system, pulmonary system, to create a significant amount of surface area available for gas exchange. The thickness of the diffusion barrier is very, very small in the respiratory system. So if we consider the diffusion barrier to be anything that stands between the alveolar space, right, where oxygen or where the gases are, and the interior of red blood cells, where, especially for oxygen, where the gases are destined to go. Okay. So everything that stands in between includes, it's this little inventory list over here. It includes a layer of surfactant, right, pulmonary surfactant on the alveolar side, the entire alveolar cell, right, the type 1 alveolar cell, all of this interstitial space in between, the entire capillary endothelial cell, right, the thickness of that, and then any plasma that happens to be sitting between the capillary wall and the red blood cell, and then the red blood cell membrane. Those are all of the barriers between this that represent the diffusion barrier. Okay? Now the total thickness of this barrier, okay, at most of these points at the gas exchange site is approximately 0.5 micrometers in thickness. And again, just to give you a little perspective, that represents, that's about 50 times thinner than a sheet of tracing paper. So we're talking about a diffusion barrier that is very, 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 very small. Okay? And that we want that to be very small so that it does not stand in the way of diffusion. Okay. So, and we talk about this at length in pathophysiology, but just as the lungs, a healthy respiratory system maximizes surface area, it has a healthy partial pressure gradient, especially for oxygen, and then minimizes the thickness of the diffusion barrier. There are conditions where you have altered gas exchange because of an alteration of one or more of these parameters. So for example, for individuals with pulmonary disorders where they have a reduced number of functional alveoli, okay, maybe the alveoli have compressed, or they've collapsed, or for any number of reasons, that's going to reduce the surface area available for exchange, and it's going to reduce or compromise gas exchange. There are pulmonary disorders where you've got chronic inflammation and damage, which leads to a buildup of scar tissue at the sites of gas exchange. And that's going to cause a thickening of the diffusion barrier. And it's going to compromise again, it's going to compromise gas exchange. Okay. And then there are some pulmonary disorders and also situations where the partial pressure gradient gets compromised. So for example, individuals who are in extreme altitudes are breathing in air with a lower atmospheric pressure, right? A lower total atmospheric pressure, which is also going to cause the PO2, or the partial pressure of oxygen, to be lower. Okay? So if you're breathing in air with a lower PO2, you're delivering less oxygen to your alveoli, and you're compromising this partial pressure gradient. Okay? And individuals with pulmonary disorders where ventilating the lungs becomes a challenge, right? Conditions like chronic obstructive pulmonary disease, where you've got a narrowing and a destruction of the airways, the delivery of oxygen to the sites of gas exchange, right, which is really the definition of ventilation, is compromised. Okay? And so that's going to compromise the partial pressure gradient available for exchange. So we talk much more about that in pathophysiology.